A really good technique I found for making binary challenges is you go to like some random GitHub repo of some previous CTF challenge, you directly copy paste their entire Docker file, and then you just change the C source code as you want.
Kind of. I personally have my own, which is... That's what I use. Basically, all this is doing is it starts at an Ubuntu 19.04, make sure that you have the 32-bit installed, gets all GCC, SOCAT, and everything going, adds the user, copies the challenge in, blah, 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 makes it work, exposes the port. And then SOCAT is basically netcat, but a lot better for challenges. If you do want to use netcat, you need to do some weird things with like making sure standard in is zeroed out before starting it. And just use SOCAT and specifically use these options and you're fine.
Yeah, so the really cool part about SOCAT is like when someone goes to connect with these options, it creates a brand new process of that binary for every user.
Yeah. Yep. That's the other thing. Netcat will connect you to one instance of the challenge and then just kill itself. Yes. So then what I do is a few things. Challenge.c. Make sure that's there, make sure that's there. Yeah. And then I should have... Yes. Change run me to the actual challenge.
Yeah, so sometimes you would use like a different script which like wraps the challenge, but in this case, you can just run the binary.
Yeah. In this case, we're going to do one that, as you say, you can run the binary. This was actually made from, or copied and pasted from my first segfault, which basically wraps the binary, makes sure it crashes properly, and then prints the flag. But yeah. In this case, you can make a makefile, which I'm just gonna copy and paste this part. And you can, everyone, I assume, has done some form of makefile before. Yay, nay. All right. Yes, Tim.
Well, I mean, I literally only started learning C through MonSec, so
Solid. Well, this is a makefile. This is basically an automated script to specifically for compiling binaries. You don't have to do it as modular as this. It's just easier. So up here, all I'm doing is specifying the variable cc, which in this case is the compiler flags, which are this one, and then the name that I want the challenge to be output as. I have, ignore the fact that the -o is in flags. It's fine. I'm a professional. Basically, this name is just whatever will be run here. And then literally all this is doing is as soon as you do the command make, which is run at this point, it will execute the command that is constructed by just copy and pasting all this stuff in. A few things to note here is no stack protector is very important because that basically turns off majority of the memory protections. -M32 ensures that it is compiling as a 32-bit binary, even if it is on a 64-bit machine. And then this defortify thing is just because I've had trouble with fortify earlier. I don't entirely understand what fortify is. I just know that it's been an issue. So turn that off in compiling. And then all I need to do...
or don't, if you want to make the challenge harder.
All that. Maybe fortify is part of it. Yeah. So then, all we need is an int main. Just some basic ones that pretty much every basically every C program will use. H. So yeah, that's your very basic C program. If we do this, you can connect to it and then it'll immediately exit. In this case, because it's the one I have most experience with, I'm going to do a buffer overflow challenge. One thing to note with these is that compilers are designed to be very, very, very optimal. They are designed to mess with your code in ways you didn't know your code could be messed with, so that it saves a few more seconds in this weird little edge case.
Seconds. Like
Seconds.
nanoseconds. That's what they're optimized to.
Yeah, well. As such, one thing that made all of my initial challenges fail is I put the vulnerability in the main function. So I did something like character buffer, let's say 64, printf buffer. Something like that, right? Yes. So all the things going wrong in this program at the moment, most notably, since I'm using get and not something like fget, that implies this is a buffer overflow challenge. But if we were to actually run this using the make, oh yeah, I already made the make file. Look at me. Never mind, this doesn't work. Why would I assume a live demo works?
You're probably in the wrong directory.
I am very much in the wrong directory. Thank you. Whoops. Still, does that work? That works. Wonderful. So yeah, if we actually decompile this challenge, we will see that the idea behind buffer overflow is you overflow it, you change the return address, right? But down here, there isn't immediately like a do the printf and then do some other stuff and jump straight into the ret like you would normally expect a buffer overflow to do. There is all this stuff. Don't know why it's there. Don't know why the compiler does it. But if we were to instead do something like void vulnerable, and we were to put all that stuff in here, and then just call vulnerable, exit out of here, make it again, we can see what the new compiled binary looks like. Oh, this has main, call to vulnerable. We still have leave and stuff here, but we can see that it didn't fuck up as badly as it has previously. Basically, we should have seen that it's just a hell of a lot easier to do because it doesn't immediately mess with things. So word of advice, always put it in a separate file.
Wait, so is it just straight up impossible to do a buffer overflow challenge if it's all done in the main function, or like?
No, so with most modern implementations of GCC, GCC just does special things to main when people aren't looking at that, right? In older versions of GCC, you'll find that it doesn't do those optimizations, and you can put everything in the main function, and that's fine. That's what Protostar does. Protostar is built on an older version of GCC, so everything's in main. It's good to go. It is just like modern versions will add things like these leave instructions, which I don't know why that one's there. It hasn't been previously. Yeah, things like these leave instructions, which mess with the registers. So you have to fix those before you can jump into the just straight return address.
So the actual problem, like, so is it just that it's unpredictable where the
That's what I'm doing.
where the return address is going to be? Is that the main problem, or is there more to it?
It's not. It's not so much. It doesn't know where the main return address is. It's just that you have things messing with memory before the return address. So instead of you when I hit the return address, it will mess with it a bit more. And I realized why my example has screwed up a bit more. Why does this change? Well, let's do that. There we go. There we go. So I actually just copied from the wrong location. See how when I call vulnerable here, I have this leave instruction? If I were to try and buffer overflow here, this leave instruction is designed to basically make it easier for it to jump back to the OS, or at least that's my understanding of it. So it will mess with the stack frame a bit more and basically remove the stack frame, right? Whereas when it's in just a normal function, it does it as you expect it, where it will just get rid of the first few things on the stack and then return to whatever the previous function is, effectively removing, like this part is basically just removing the stack frame. The thing that I did wrong, and the thing why this has why this changed up here, was I forgot a few more flags than I needed. So like before, stack protector to get rid of most memory protection things, M32 to actually get it to be a 32-bit integer. This -0G is for optimizing binaries. Basically, it tells it, act like you're in the 90s, don't optimize, don't do weird things like these leave instructions because I don't want it to. It will still, it doesn't do it in main here, but and then this one is basically just saying that you can execute stuff from the stack. So if I wanted to put shellcode in here, I could, and then jump to the stack and let it execute from there. If I don't have this on, it will default to not allowing the stack to be executable, meaning if I put anything onto the stack and then I try and put my program counter to point to the stack so I can execute my shellcode, it will, I'm not sure if it's stack smashing or it will throw some kind of error just saying, I can write to this memory, I can't read it, I can't execute though. No pi is just a means to not enable pi, quite literally. So if we actually have a look at checksec, that is disabling this thing. Pi is a position-independent execution system, which it's basically ASLR on steroids. You can think of it that way. Be sure to get rid of that. And that reminds me of the last thing that I forgot, which was disabling ASLR. Because if we were to actually run that at the moment, and if I were to do something like there we go. Every time I run this, it will be at a different position, even though I've turned off all of these memory protections, because I have forgotten the one of the most important memory protections, which is disabling ASLR. Which I, in all honesty, just copy from Stack Overflow whenever I do it. So copy that. Ooh.
But Daniel, you turned off all the security protections on the binary. Why is ASLR still on?
ASLR is still on because it isn't done at compilation time, unlike Pi or the NX bit or anything like that. It is done by the operating system. Basically, you'll notice that whenever I'm referring to a variable here, it's always using an offset. That's to let the OS then be able to shift where it is in memory at runtime to basically add more randomness to make it harder to be able to like do shellcode, shit like that, right? It means that you can't just reliably jump to the same address. In terms of Linux, I believe it's done in the kernel. So when you turn it off in the kernel, you turn it off for the entire system. In saying that, I've been looking into Windows recently, and it looks like Windows does ASLR on a case-by-case basis for its executables, which is interesting, to say the least. Yeah, just jump into, whoops.
So you can't disable ASLR on one binary, then put it onto another computer, and it's on the computer-by-computer basis.
For Linux, yes. Or for Unix-based systems, yeah. So what I just did then, this command to write into proc system kernel randomization, randomize VA space, that has turned off ASLR on every binary. So if I then exit out of this and I run challenge, you'll see that every time I run it again, it will give me the same memory address, which is the memory address of buffer here. If I were to jump back in and I am to write 2, I don't know why it's 2 and not like 1, but
I think it's like different levels of protection. Like 1 is like 50% protected or something.
why the fuck is that a thing? Anyway, we can see that it changes again. Yeah, just write whatever. That's basically just the template you can use for being able to read it. And then what I like to do, for mine at least, is it's bad and I should feel bad, but normally in something like this, I will have like, say, a integer that you have to change. And then once you successfully change it, I literally just have an if statement with system cat flag. And it works. It's not the safest, but also this is a binary challenge. You really expect it to be safe. Yeah.
Yes, so basically there's like different difficulties of binary challenges, right? So some of them cat the flag if you modify some important variable, And modifying important variables is like a security vulnerability. So like it's still like a legit challenge. But some challenges go the extra mile and don't actually have like a cat flag, and you need to completely like convert the program into a shell yourself.
Which is quite
Which is a
literally
bit annoying.
just, if you were to do something like that. That in itself is a challenge, because you would be, actually, that is not entirely in itself a challenge. But if I were to add one last thing that is really fun to do, in C you can actually also write inline assembly, which is fun. In this case, by adding this here, I can remake that, and then, what is it, wrapper? I forget how to use wrapper, but, oops. Yeah. Nope.
You got to give it the file.
Okay, I didn't get it entirely wrong. But yeah, if we were to, say, comment this part out, this is just a neat little trick you can do, and remake the file, we can see that it doesn't find any instance of jump ESP. But we can add that back in, remake the file, and then there is all of a sudden an instance, because we've added this inline ASM.
So what is jump ESP?
Thank you. I was just about to get to that. You would use jump ESP to jump to the stack pointer, or basically to jump to the stack. Say in this case you've overrun the return address, and you've also put your shellcode on the stack. How do you actually get there? Well, as we said earlier, up here, with ASLR turned on, you don't always know where it's going to jump to. You don't always know where the stack is located. That's what I meant to say. But it doesn't matter, because the ESP register holds a pointer to the stack, holds the stack pointer, right? So it has a pointer constantly in it to say where the start of the stack is. So if you were to have shellcode on the stack, then if you were to somehow jump to ESP, then you would be able to jump to that shellcode. And that's just the vulnerability that we're introducing here. We're just ensuring that there is some point in the binary that you can jump to ESP with. Now, in saying that, this vulnerability does exist in the wild. It's not just as arbitrarily put in as it is here. Because think about like Python, for example, it has to execute from memory. So somewhere in Python's source code, you will more than likely find at least one or two or thousands of this jump ESP instruction. And if we actually have a look at...
I think I disagree that you would find jump ESP, because that implies that Python like puts shellcode onto the stack, which is a bit contrived.
It's surprisingly common, I think.
But maybe because it might be like efficient for like...
Yeah. And something I haven't personally looked into, and I'm not saying it definitely does this, but if we have a look at checksec on not Zom, if we have checksec on the Linux release of Zoom, we will see that it has none of the memory protections, including pi or anything like that. And the only instance I can think of that it would need to do that is if it's messing with its own execution its own code flow execution using the stack. So
We can try using Ropper.
actually, yeah, let's do that. Yeah.
So Daniel, is it possible for like if you don't do like the ASM jump ESP, like you don't specially contrive things in your source code like that, is it still possible for Ropper to find anything?
Yes. Because what this is doing here is it's putting it into the code section. But, I mean, everything in a computer is hex code, right? So, what is it? It's very likely that you could find the hex code equivalent of jump ESP, which hopefully, nope, I cleared it earlier. You could very easily find the opcodes that would point, like, that would be decoded as jump ESP in something like the data section. You could find, like, just a string just happens to have the hex code, and if you jump to that particular string in memory from, like, a return, then even though it's not intended as code, it could still be read as jump ESP.
Daniel, is it possible to exploit a binary even if it has pi and like stuff enabled?
Yes, isn't that what I'm doing here?
No, because you disabled pi on like a bunch of stuff, and like the.
Oh, you asking for pi specifically, not just memory protections in general.
Okay, I mean like all the things, right? Like if you don't add all those special flags which say, I really want to be insecure, I swear I really want to be insecure, please make me insecure, is it still possible?
Of course, yes, there is always a way to get around memory protections, even if you have everything enabled. It just depends how much of a nation state you want to be. So for instance, the NX bit, right? That is what this section does, which says, don't make the stack executable. What if we never touch the stack in terms of writing shellcode? That's where return-oriented programming comes in, or ret-to-libc. It's where you only execute code that already exists in the binary, but you make it do what you want it to. And fun fact, RUP is actually Turing complete. So you can, provided you get certain gadgets, you can actually do whatever the hell you want without ever touching the stack. Similar thing with the stack canaries, right? If you enable stack canaries, then that basically what they do is if you try to override a buffer and override the return address, before it returns, it will check to see if the canaries have been overwritten. And if the canaries don't, the value of the canary doesn't match the value of the original canary, then it will exit the program and never let you return. You could very easily get past that just by, either knowing what the canaries are, using like a format string attack, you can learn the layout of memory if you want to go full nation state. Or what if you change the value of the original canary? If you could find a way to do that, then it doesn't matter what your overwritten canary would be, because it would be comparing to another overwritten canary. I don't know how to do pi myself. That is something I need to look into. And then even ASLR. If any of you are looking to do, software security, FIT 3173. The first assignment of that, legitimately, there is a question in there that asks you to get a shell on a vulnerable program despite ASLR being on. Because all ASLR does is it randomizes where in memory it's put, right? So basically all it does is it adds an offset to the entirety of something in memory. What if that offset is, because it's random, it could be any value, right? What if it's 0? Or what if it's 1 or 10? What if it's a very low number? Then it's basically like if if ASLR was never on, and you will get a shell. ASLR doesn't entirely protect against corrupting memory and shellcode and whatnot. It just makes it a lot harder and a lot less likely. I think my attempt at getting the shell took about 30 minutes of restarting the program 10 times a second. That took 30 minutes to get a shell. That's why ASLR is useful.
Maybe you can open another shell and run just Ropper without any search on the original challenge binary. Just to see what sort of random instructions pop up, even if you don't have the contrived ASM. Right, and like anyone can do this same stuff at home, right? Just make a C program, install like all the programs you see here, like Ropper and all that.
Ropper, I think, is pip, if I'm not mistaken.
Sorry?
Ropper is like Home Tools, where you can just get it from pip. Or I think there's actually an AUR. Never mind.
Ropper is just a random Python program. It's like
yeah. And yeah, if you were to do it without search in particular, then you would get broken ones, because I went to the wrong bloody directory again. Yeah, you would see all of these gadgets. So this is basically every set of instructions within the program which end in either a call to something or a return. Because at the end of the day, return is just the same as call. It's just return has a specified location, call takes a register to call into.
Wait, hang on. I've just run it on my computer and it like returned almost instantly.
Well, what?
It's because you're using VS Code.
Hold on now. Fuck off.
Alright, hang on. Let me just share my screen.
Oh, yeah? Let's see.
Alright, so if we actually do try to search for jump ESP, there's nothing there. Sorry.
Oh, all that build up for nothing.
But if you just search for all gadgets, there's a few of them.
There's a shit ton.
I mean, in any program, there's going to be a bunch because it needs to have return statements, right?
Yeah. Hold on. This is a 64-bit program, right?
On my machine, yes.
Yeah. So wait. Oh no, it's ESP is still the same between 32-bit and 64, right?
I mean, there's, right, if you look up x86 registers, there's a really cool diagram on Wikipedia. Right, it's on the x86 page. And it's just some random diagram somewhere, I think. Hang on. Yes, this diagram. I love this diagram. It makes things so clear. So we have, can you guys see the cursor?
Nope.
All right, but basically we have you can see the highlighting though, right?
Yeah.
So ESP is just the 32-bit version of RSP. It's like the lower 32 bits. So like.
So if you were to tell Ropper, look for RSP, would it return anything?
Yeah, so I think like the way you do that is anything with ESP, go. And then it says, oh, there's all this stuff with.
What I'm saying is, like, if you were to specifically say RSP instead of ESP, does that change things? Or does it translate for you?
Oh, what if we search for RSP, right?
Yeah.
I think it sometimes does the translating, but it doesn't seem to be doing it this time. Yeah, I don't know. It doesn't seem to be doing it this time.
No.
It's fine. But yeah, so
Yeah.
binaries
Thanks for
have
sticking around
code.
Yeah. Thanks for sticking around to see us fail our way through making some CTF challenges. If you do want to actually participate in that community thing, then please let us know. We will most definitely take anything people get.